Hi everyone. Today we're going to talk about section 7.3, which is one of my favorite sections of the methods of integration chapter. And hopefully it will become clear why I like it so much as we go through. But I think this is a lot of fun. It also requires a certain amount of pattern recognition that is going to be facilitated by the fact that you'll be working off of notes when you perform these integrals on your own. So let's get started. One of the most important ideas in mathematics is that we can calculate the area of a circle. So the area of a circle is pi r squared. And we also know that the function of a circle, or at least a half circle, if you had some half circle of radius r centered at the origin, then the equation that generates this semicircle is y is equal to the square root of r squared minus x squared. This comes from the fact that the circle equation is x squared plus y squared is equal to r squared. And you solve for y, take the upper branch, and this is what you get. So here's a more complicated question. How would I find the area if instead of looking at the entire semicircle, I was looking at, say, the piece that went between A and B? This is the sort of thing that turns out to be important in application when you're using circles. What we learned at the beginning of chapter 6 was that a region like this, if we want to calculate the area, we write down an integral. And the integral we're going to write down for this would be something like a is equal to the integral from a to b of the square root of r squared minus x squared dx. Very natural sort of integral to be able to want to solve. The problem is, none of the techniques that we have available to us right now will let us do this. If there was an x right here, then we'd be okay because we could use a u substitution. But there's not an x. So what are we going to do instead? We can't use, say, integration by parts, because if I take the derivative of this, I end up with a fraction that has that in the bottom. And the derivative of the interior is going to turn out to put an x in the numerator. And then we're also going to have another x that comes from integrating the dx. So parts doesn't work. So no u substitution and no parts. And it's not the derivative of an inverse trig function. So the problem here is I've got this square root that I can't get rid of using any technique that we know, and there's no substitution that gets rid of it. So the big question is, can we get rid of the square root? We're going to address this problem by converting this expression into another expression where it's just a single function squared, and then the square root and the square will cancel each other. So how could I convert r squared minus x squared into something squared? Well, if that x was actually not an x, but instead it was a sign, we could use the Pythagorean identity. So if that x was a sign instead of an x, then we would have a sine squared, and we could do 1 minus the sine squared is equal to the cosine squared. So if we had that r squared minus, say, r sine of u squared. So I'm just going to switch the problem into a different problem here. So replace x with this r sine u, then what would happen? Well, this would be r squared minus r squared sine squared of u. The r squared would pop out, and we'd have a 1 minus sine squared of u left over, which is really just a cosine squared. And so the square root of this will cancel into r cosine u. So if it was a sine, we could use the Pythagorean identity to get rid of the square root. And so we're just going to make this substitution. So this is the key idea behind the entire chapter, is that when I see a pattern where I could use a Pythagorean identity from trigonometry, I'm going to make a substitution that lets me use that identity. So let's go back to the original problem here, but I'm going to use fixed numbers this time. So let's find the area between x is equal to -1 and x is equal to 1 underneath a circle of radius 2 centered at the origin. And I don't really want a circle here, I want a semicircle. So this is the same question that we began with. The idea here is that I have a circle that looks like this, and I want to know the area between here and here. So I'm going to write down the integral that represents that area. So that's the integral from -1 to 1 of the equation that defines this semicircle, which is 4 minus x squared dx. And now I'm going to use the observation that we made on the previous slide, which is that if x happened to have a sign that let us use the Pythagorean identity here, then the square root would go away. So this is going to be what we mean by an inverse trigonometric substitution. We'll let x be equal to 2 times the sine of u. And this is called an inverse substitution because instead of having u be equal to a function of x, here we're replacing x with a function of u. dx is equal to 2 times the cosine of u du. See, we get a replacement for x and a replacement for dx without needing to solve. And what we're going to do now is, notice that I chose the 2 here so that when I replace x, I get a 4 in front of this term as well. The last thing I need to do is I need to figure out what to replace -1 and 1 with. In order to do that, I'm actually going to have to reverse this expression into an expression for u instead, because remember that these are x values. So this would say that u is equal to the arcsine of x over 2. And so that means for the limits that we're using here, u of -1 is equal to the arcsine of -1/2, and u of 1 is equal to the arcsine of 1/2. So the arcsine of -1/2 and the arcsine of 1/2 have to fall in the interval from -π/2 to π/2 because that's where the arcsine is defined. And that means that we're working now from, if the sine is -1/2, then we're working from -π/6 to π/6. And so with this substitution, I can completely transform this integral into the following. The integral from -π/6 to π/6 of the square root of 4 minus, not x squared anymore, but 2 sine u squared. And then the dx is going to get replaced by cosine of u du. And all of this is going to turn into 4 times 1 minus the sine squared of u, cosine u du. And there we get to use the Pythagorean identity to replace that with a cosine squared, which is going to get rid of the square root. The integral from -π/6 to π/6 of the square root of 4 cosine squared u times another cosine u du. The 4 gets rooted into a 2. The square root of the cosine squared is just the cosine. And there's another cosine u right here. So this is 2 integral from -π/6 to π/6 of the cosine squared of u du. And now we can use the techniques that we learned in the last section to finish this problem up. So this is now a problem from 7.2. Since I'm trying to show the idea right here and not the integrals all the way through, I'm going to leave this problem where it is. And I'm going to assume that when you see a cosine squared by itself, that you remember that you have to use a half angle identity to solve it. So I want to get on to the other types of integrals where this idea of replacing x with a trig function makes an integral that can't be solved into one that can be. Now let's look at the broader picture in terms of the sort of patterns that we can find where we can use this trig substitution idea. Generally, what we're going to look for are going to be square roots with Pythagorean-like quantities contained inside. And we're going to take advantage of the Pythagorean identities from trigonometry to use them. So there's 3 that we have to be concerned with. When we see an expression that looks like 1 minus x squared, that should remind us of the Pythagorean identity 1 minus sine squared of u is equal to cosine squared of u. When we see something that looks like 1 plus x squared, we should be reminded of the identity tangent squared of u plus 1 is equal to secant squared of u. And when we see something that looks like x squared minus 1, we should be reminded of the identity secant squared of u minus 1 is equal to the tangent squared of u. Now, when can we use these identities? When we see expressions that look like the following. If we see something that looks like a squared minus x squared, then we're going to make the substitution x is equal to a sine u, because that is going to let us take the a squared minus x squared and reduce it to just a single cosine squared, so the root disappears. Likewise, when we see something that looks like a squared plus x squared, we're going to make the substitution x is equal to a times the tangent of u. And when we see something that looks like x squared minus a squared underneath the square root, we're going to make the substitution x is equal to a secant u. In each of these cases, the substitutions are going to allow us to destroy the square root, which is going to allow us to use other techniques of integration to work. So now let's look at some examples of how this works in practice. If you have something like the integral of the square root of 9 minus x squared over x squared dx, the first thing you should always think of when you see an integral is, can I do this integral with substitution? If you can use substitution, it's always easier than trying to do it with this inverse trig idea. But you'll notice here that there's no obvious idea for what u should be. If u is equal to 9 minus x squared, then du is going to be negative 2x dx, but the x here is on the bottom, not on the top, and it's a squared term. So u substitution is not obvious and immediate, so I'm going to move on to the next idea, which is trig substitution. So you can see in this one that we have a trig sub-like quantity right here, 9 minus x squared. What our pattern tells us is that we should be considering the substitution x is equal to 3 times the sine of u. So everywhere I see an x, I'm going to replace it with 3 sine u. And I also need to replace the dx. Dx is equal to 3 cosine u du. And just because I might need it when the problem is over, I'm also going to look at the relationship where u is a function of x. So u is equal to the arcsine of x over 3. So armed with these substitutions, let's transform this integral into something we can actually solve. After substitution, this becomes the square root of 9 minus 9 sine squared u over 9 sine squared u, and then dx becomes 3 cosine u du. Now, using the Pythagorean identity, which is the entire reason that we did this, is so that we could drop the square root here, this is going to become the integral of 3 times the cosine of u. And on the bottom, we have a 9 sine squared of u, and then we have a 3 cosine of u du. So how did I get from here to here? If you factor out the 9, the square root of 9 is 3. 1 minus the sine squared is equal to the cosine squared, but the square root of cosine squared is the cosine. The entire reason we used this substitution was so that the square root would vanish in our computation. So where does that leave us? We end up with an integral that looks like cosine squared of u over sine squared of u. And that's equal to cotangent squared. Now, there are strategies that we can use when we have odd powers of tangent or even powers of secant. This is a cotangent squared. There's no obvious way that we learned in the last section to proceed here in terms of powers of the functions. So instead, we have to be a little bit more clever. What we can do is replace the cotangent squared with 1 minus the cosecant squared. And that will give us integrals we can solve. So if we use the identity that says that cotangent squared of u is equal to cosecant squared of u minus 1, then this integral becomes cosecant squared of u minus 1 du. And I know the integrals of both of those things. The integral of the cosecant squared is minus the cotangent. And the integral of 1 is u. Here is where there's often mistakes made because we're not finished with this problem. It's an indefinite integral, and we have these u's floating around inside here. But I needed functions of x. So what was u equal to? If we go back to the previous page, we can see that u is the arcsine of x over 3. And that means that all of this becomes minus the cotangent of the arcsine of x over 3 minus the arcsine of x over 3 plus c. And we can go one step further, because when we have expressions like this, where we have trig functions of inverse trig functions, we can use the fact that inverse trig functions produce angles of right triangles and have trigonometric relationships to compute this as a function that doesn't have any trig functions in it at all. This is called the right triangle method. So the arcsine of x over 3 is some angle theta. And theta is the angle that has the sine x over 3, which means opposite over hypotenuse. And so by the Pythagorean theorem, the last side relating to theta is 9 minus x squared. That should look familiar, because this 9 minus x squared is the same 9 minus x squared that appeared in the original statement of the problem. What is the cotangent of theta for this triangle? Because remember, this is a theta. So what's the cotangent of theta? Cotangent is adjacent over opposite. And so this is going to be equal to minus the cotangent of this theta, which is adjacent over opposite, minus the arcsine of x over 3 plus c. And that's the end of the problem. This move where we have trig functions of inverse trig functions and we replace them with functions of x using the right triangle, that's one of the standard things that happens in these problems, just like in section 7.2. You should see here that inverse trig substitution is typically going to lead to situations where when we come back, we have to use inverse trig functions, and we're going to get things like trig functions of angles. So the right triangle technique is something that you should practice. So the challenge in many of these questions is putting a problem that looks like an inverse trig substitution into a form where you can, which is an algebra challenge. So let's look at an example where we have to work through putting the problem in the right form first. If I have the integral, say, of x to the third over 4x squared plus 9 to the 3 halves dx. First thing is, don't get intimidated by the 3 halves, because remember, that's really secretly a square root, because what this represents is the integral of x to the third over the square root of 4x squared plus 9 to the third power, which means it's actually of the correct form for inverse trig substitution. So if we can drop the square root, we can just apply the third and we can integrate like normal. The problem is, I would like to replace this argument here with a trig function that I can use to collapse the square root. But this doesn't match any of the patterns that we saw. It looks kind of like a squared plus x squared, but the x isn't by itself. So I'm going to make the x by itself. So I have to manipulate the form of this before I can do the trig substitution. The form that I'm after is x squared plus a squared. And then if I can get that form, I would like to let x be equal to the tangent, or a times the tangent of u. But in order to put it in this form, I have to use algebra to do so. So here's what I do. I am going to take a 4 out of the argument. So I'm going to rewrite this as the square root of 4 times the square root of x squared plus 9/4 all to the third. I can do that because if I pop a 4 out of here and I pop a 4 out of here, well, 4 times 9/4 is equal to 9. So factoring out a 4 leaves a 9/4 behind. And now I've got a correct form, because the a here is 3 halves. A squared is 9/4, so a is 3 halves. So that square root of 4 on the bottom is really a 2, but 2 to the third is an 8. So let's put a 1/8 out here. And on the bottom, we're going to get a square root of x squared plus 9/4 to the third dx. And now we can use our substitution. X is equal to 3 halves of the tangent of dx is equal to 3 halves times the secant squared of u du. With that substitution, we get this integral. Okay, x to the third now is this to the third. So we're going to get 27 over 8 tangent to the third of u. That's what the x third became. On the bottom, we're going to get, well, the whole reason we made the substitution was so that we could collapse that square root. So this is going to be the square root of 9/4 tangent squared of u plus 9/4, and then dx gets replaced by this stuff, which is 3/2 secant squared of u du. Which looks like a mess because you've got fractions running all over the place, but it's actually not that bad. All right, so let's finish up the algebra here so that we can get on to the integration. The first thing I'll notice is that I forgot to put the third on here that's supposed to be here. I can add it back here too. So this is equal to 1/8 the integral of 27/8 tangent to the third of u. On the bottom, all of that is going to turn into a 3/2 secant u to the third times 3/2 secant squared u du. Now the reason that happened was because I pulled out the 9/4 and I was left with a 1 plus tangent squared, which is a secant squared, and the square root of secant squared is secant. The square root of 9/4 is 3/2, and all of that is to the third. So this is going to be 1/8 times the integral of 27/8 tangent cubed over 27/8 secant cubed times 3/2 secant squared du. Now we have to do the algebraic collapse that makes this into a problem we can actually solve. Notice here nicely that the 27/8 kill each other. And then I can take the 3/2 and stick it out here with the 1/8. And I can cancel 2 of the secants here with 2 of the secants down here because these are on top and these are on bottom. And that's going to leave me with the integral of 3/16, and I have a tangent to the third of u over a secant of u du. And now we're back in the realm of section 7.2. The trick you can use here is a pretty typical one, which is if you have no other idea how to proceed, convert it to sines and cosines and see if that fixes anything. If I convert this problem into sines and cosines, what I'm going to end up with is 3/16 the integral of sine to the third of u, and then secant is 1 over the cosine, but when you divide, you flip it, and so it's going to cancel one of the cosines that's on the bottom of this tangent cubed, and so you're going to get a cosine squared down here. Now we can use the idea of popping out one of the sines and using it as the du. For the substitution, u is equal to the cosine of x. So this is going to be 3/16 the integral of sine squared of u over cosine squared of u sine u du. I can convert this into 1 minus the cosine squared of u over the cosine squared of u times the sine of u du. And now I'm solidly back in the material of section 7.2. because I can finish this problem by letting u be equal to the cosine of, I'm sorry, we shouldn't use u, we should use a new letter, v be equal to the cosine of u, so that dv is equal to minus the sine of u du. And yes, these problems tend to be kind of long. So with that substitution here, with this v substitution, what do I get? 3/16 the integral of 1 minus v squared over v squared times minus dv. And that's equal to 3/16 times the integral. Splitting the fraction and multiplying in the negative sign is going to get us 1 minus 1 over v squared dv. And that is 3/16 of v minus 1 over v plus, because of the chain rule. The integral of 1 over v squared is negative 1 over v plus c. But of course, v was this. So I have to replace v with the cosine of u, and that gets us 3/16. V is the cosine of u. 1 over v is the secant of u. I'm still not done because, of course, u was also equal to something. We can go all the way back to the beginning of the problem to see what u was equal to. Oh, well, there's x. X was 3/2 of the tangent of u. So if x was equal to 3/2 of the tangent of u, then that means u is equal to the arctangent of 2x over 3. And so making that substitution back in, we end up with 3/16 of the cosine of the arctangent of 2x over 3 plus the secant of the arctangent of 2x over 3 plus c. And now I have to use the triangle method if I want to finish putting this back into the form where we have x's. So I'm going to stop here on this example and not continue with the triangle method because we've already done 3 slides full of math to get to this point. The last example I want to talk about is one where it's not obvious that we can use a trig substitution. And so we're going to do algebra to get it into trig sub form first. If we're looking at a problem like the integral, say, of x over the square root of 3 minus 2x minus x squared dx. There's not going to be an easy u substitution here. And the reason that there's not going to be is if I try to take this as u and I take its derivative, I don't just get an x, I get negative 2x minus 2. And that's going to screw up our replacement of x for the dx du step. What makes me think this is a substitution, and in particular an inverse substitution problem, is that I still have a square underneath a square root down here. It doesn't look like the right form because it's not a squared minus x squared. So what I'm going to have to do is algebraic manipulation so that it looks like something squared minus something else squared. And the tool we're going to use to do that is completing the square. Or if you like, you can use the quadratic formula, but that's more work. So I'm going to notice that 3 minus 2x minus x squared, I could make this into a perfect square if there was a negative 1 right here. Of course, to do that, I have to add 1. Now, how do I notice that? Well, if I take out a negative sign, I get x squared plus 2x plus 1, and that's a pretty standard perfect square form, so that this entire expression is 4 minus x plus 1 squared. And that's almost what I want. It's still not x squared. It's x plus 1 squared. So this integral is the integral of x over the square root of 4 minus x plus 1 squared dx. And we can almost use a trig substitution. Almost. To me, this looks like an inverse sine substitution. But we have this 1 in here we've got to get rid of. So I'm going to do a preparatory step where I'm going to let u be equal to x plus 1 so that du is equal to dx. So this is just a really straightforward u substitution that I'm using to prepare the problem. After I do that, I get the integral of u minus 1 over the square root of 4 minus u squared du. Now, where did the u minus 1 come from? It came from the fact that if u is equal to x plus 1, then x must be equal to u minus 1. Well, this is an integral I can use trig substitution on, because that is an inverse sine substitution. So what is the substitution that I want to make here? Well, if I look at the pattern, I can see that what I'd like to have happen is that u is equal to 2 times the sine of v. And du is going to be equal to 2 times the cosine of v dv. And that gives me the integral u, which is 2 sine v minus 1 over the square root of 4 minus 4 sine squared of v times 2 cosine of v dv. I can break the top into 2 different integrals. So this turns out to be 2 sine v minus 1 over, let's see, the bottom turns into 2 cosine v. Again, the 4 factors out. 1 minus sine squared is the cosine squared. So cosine squared, if I take the square root, turns into cosine. 4 that I factored out in the square root turns into a 2. Oh, that's cute. These cancel. So you end up with the integral of 2 times the sine of v minus 1 dv, which is just negative 2 cosine of v minus v. And then you go through the process of unsubstituting everything that you did to get here. Since u was equal to the sine of v, that must mean that v is equal to the arcsine of u over 2. And then I can substitute it back once more to get rid of the u's, because remember, the u here was the preparatory substitution that I made that is equal to x plus 1. Finally, using the right triangle method, we can take this and we can actually get an expression for the cosine of the arcsine. So all of this is a theta. The triangle that goes with it looks like this. There's a theta here. The opposite side is x plus 1. The hypotenuse is 2. By the Pythagorean theorem, this side is 4 minus x plus 1 squared. And that means that the cosine of that angle is equal to the adjacent side over the hypotenuse. And all of this is negative 2 times the square root of 4 minus x plus 1 squared over 2. That's the cosine of the arcsine of theta minus the arcsine of x plus 1 over 2 plus c. So don't get intimidated by the fact that these are so long. These problems do use a lot of technique, but they're also extremely important because areas underneath objects that look like 1 plus x squared or 1 minus x squared or x squared plus 1, these are the sorts of functions that arise when you're working with circles, ellipses, and hyperbola. Those are the sort of the basic functions of geometry. And so physical situations, engineering problems, architecture, you're going to see lots of circle, ellipse, and hyperbola geometry. And the only way we can use calculus on those things is with this particular technique. Hopefully I haven't scared you too badly here. This technique is going to involve practice like the rest of them, because the idea of manipulating trig functions is at the core of what we're dealing with here. And there's an art to that when we don't have the patterns that we usually look for. The idea of trying to take a trig function and turn it into sines and cosines in order to find a pattern. The idea of looking for places where you can productively apply a Pythagorean theorem. All of these are the techniques that we learned in 7.2, and now we're applying them in a context where we're really substituting 7.3 material to get 7.2 material. So the upshot is that we have patterns that look like a squared minus x squared minus a squared, and x squared plus a squared. Those let us make substitutions like x is equal to a sine u, x is equal to a secant u, and x is equal to a tangent u. 1, so that we can kill the square roots off, and 2, so that we can transform a 7.3 type problem into a 7.2 type problem. All right, so this has been kind of a long video, I recognize, but this is one of the core techniques of working with some of the most important functions that we have available to us as scientists and mathematicians. So take the time to practice these, work your way through the examples to the end, and please try to practice the right triangle method of converting trig functions of inverse trig functions into expressions of just x and roots. All right, so I'll see you for the example video.